Welcome to Statics. This content corresponds to the beginning of learning about moments, and it's an application of how you can break up a force in two dimensions and more quickly solve a moment of a force problem. So here we have a force of 100 newtons um, applied to the point at the end of this beam, which is stretched out from the wall at O. And our objective is to determine the moment of the force about point O. So there's two ways we can go about it. We're going to do both ways, and we're just going to work this problem a little bit slowly. So first of all, remember that the moment of a force is equal to, it corresponds to the action, or I guess the effect of the force on the point O. And in order to figure that out, you have to write a vector that connects the point you're thinking about to the line of action. So in this case, our point is 0, that's the moment we've been found, and we need to connect it to the line of action. And so if I do that, then that is my R vector. And so always keep in mind that R goes from the point to the line of action of F. And I connected it directly with where F is hitting that beam, but you can extend that line of action in a few different ways that we'll see in a moment. So we have two ways of solving the problem. Method one is to use R cross F, and that will be our moment. And we'll do that last. The second method is to use this sort of principle of moments method. And that's what I'd like to illustrate to you right now. So why would I use this method? Well, it's in two dimensions. I can pick up pretty quickly that I can pinpoint. Well, you'll see. All right. So let's go ahead and work on the principle of motions. So to do that, let's go back up to this diagram, and I just want to clean it up and get rid of that R vector, if it'll let me. It probably won't let me. All right. So over here, what I would like you to notice is that we can think about this blue force, F equals 100 newtons. We can think about it in terms of its x components and its y components. And so let's just do that real quick. So what I'm saying is we can think of the y part of F as doing that, and the x part of F is doing that. So let's think about that y part first. So if I extend the line of action of the y part of that force, all I've done is extend the line of action. What I observe is that I have the perpendicular distance that connects point O to the line of action. I have that, and its value is 5. All right, so let's articulate that. So what I have noticed is that the moment at O can be thought of as equal to two pieces. So piece 1 is going to be this 100 Newton force times the value of it that's going in the y direction. So that's the part that's going down, multiplied by 5 meters. Why 5 meters? Because that's the perpendicular distance, and moments are equal to the perpendicular distance times the force at its simplest level. Now, having said that, we have to think about the sign of this. We have to think about whether it's causing motion that is clockwise, which is defined as being negative, or motion that is counterclockwise, which is motion that's defined as being positive. And so to do that, I want you to take your right hand and line your right hand up going from O to the line of action of the force. So you are imagining you were doing this with your hand. Your fingers are going right here. And now curl your fingers along the direction of the line of action of force. And what you will notice is that is a clockwise motion. Your thumb is pointed into the screen, and therefore this is negative. Okay, so we haven't finished this problem. What we now need to do is think about the x part of the force. So this was the y part of the force. And now I want to think about the x part of the force. All right, so we're going to have to add to it the x part of the force. So the x part is, we have a 4/5 times 100. And so now let's return to our figure. We're now thinking about the x part of the force. So let's try to find a nice peculiar color. So you can pick this out. We've switched to bright purple. So the x part of this force is right there. And I'm going to extend its line of action, because that's always a helpful thing, and it's going generally in that direction. And now I'm looking to see if I easily have the perpendicular distance between O and the line of action of the force. And I do have it. It's right there. It's 2 meters. And so we will write that we would multiply this x part of the force times that perpendicular distance 2. And now we have to decide if that's a positive or negative rotation relative to O. And so again, you're playing the thought experiment of taking your hand and moving from O to the line of action of the force. So your fingers are going that way, and now curl your fingers along the direction of the line of action of the force, which is going in that direction. And you'll see once again your thumb is pointing in. It is a clockwise motion, and so we have a negative sign out in front of that. And so in summary, our moment is equal to, we have a minus 3/5 times 100 times 5, and that's going to equal minus 300. And then we have another negative piece, which is 4/5 times 100 times 2, and that is negative 160, which is equal to minus 460 Newton meters. Okay, that's our answer for this problem. This indicates its sign, or we can write that that is 460 Newton meters, and we can indicate its direction by writing a clockwise rotation right there. All right, so we have solved this problem kind of the second way using the principle of moments method. And now what I'm going to do is kind of erase most of this mess and solve it as r cross f. All right, and I think I've unfortunately erased my diagram, so I'll redraw that pretty quick. All right, so let's redraw our diagram. What I had was a piece of wall, and I had a beam coming off it and it pointing up, doing something like this. We had a force being applied to it, which was equal to 100 newtons. We have a slope of 3 to 4. We had a distance of 5 meters and a distance of 2. Okay, so now I want to use this method just to convince you that both methods work. So in order to do that, I'm going to have to write r in Cartesian. All right, so what is r? R connects the point to the line of action of the force, and I am choosing to make my r go from this point to that point. That is what I've chosen for my r. You can choose other points, but that's what I'm doing. And so I can see, if I label this as positive x and that is positive y, that that's equal to 5i plus 2j, and I have 0 in the k direction. Second, I'm going to write my force in full Cartesian coordinates. And I can see that I have 4/5 of 100, which is 80i. That was 4/5 times 100. I have a minus 3/5 times 100, which is 60 in the k direction. And I have, sorry, j, that was j. and I have nothing in the k. So now, what I want to do is I want to calculate r cross f, right, by doing the determinant. So what we do is we write I, j, k. We write our r vector and our f vector. R is 5, we have a 2, and we have a 0. We have an 80, a minus 60, and a 0. So now, if I do r cross f, I'm just going to do that below here. What we have, so r cross f equals, and now I'm thinking about the I part first. We have a 2 times 0 minus a 0 times a minus 60. That's a nothing. That's what I have in the I. Second, I think about what I have in the j. I've got a 0 times 80 minus 5 times 0. That's what I've got in the j. That's a bust. And then I have this third term, which is really all we expect anyway. So we have a 5 times a minus 60 minus 2 times 80. And that's in the k, which is equal to minus 300 minus 160, which is equal to minus 460k, which is what we got the other way. So in summary, you can break up these forces into their convenient x parts and y parts. And when you do that, sometimes you can simplify the problem. And we're going to be working a whole bunch of problems like this in class. Thank you.